I can, if you want, I'll introduce you.
Either way, whatever.
Yeah. Okay, we'll go ahead and start now. We've got a group here from University of Rhode Island, University of Washington, and Desert Research Institute for a special talk tonight. And so welcome and go on.
Yeah. Well, hi everyone. My name is Kendall Valentine. I'm an assistant professor in oceanography at University of Washington in Seattle. Originally from Minnesota, lived all around the lower 48. I'm doing some work up here the last 2 years.
My name is ERIN. I'm an assistant professor at University of Rhode Island, and I've studied salt marshes mostly in Oregon, now a little bit in Rhode Island, and up here some as well.
I'm Sophie WENSMAN. I am an assistant professor at Desert Research Institute in Reno, Nevada. And my focus has been on coastal and polar geochemistry.
So we're super excited to chat with you all today about some of the work that we have started doing here on the Copper River Delta. And so just first, I wanted to just address that we have many thanks to give to a bunch of different folks, some of whom are joining us today, both for the field support that they've provided and also lab support as well. And then of course, our various funders. So just to sort of orient you in terms of the research that we think about. So our research falls within the broader context of source to sink sediment dynamics, which is basically this framework for thinking about how material moves across the earth. So material is produced in upland sources, it is transported across the landscape, often through rivers, and then ultimately ends up in these coastal and marine sinks. And so we can sort of use this concept to think about the landscape as this continuum. And we can think about how things like water, sediment, I don't have this fully memorized. Just the things I care most about. Carbon, nutrients, energy, biomass, and contaminants move across the landscape. And so if we zoom into our coastal sink deltas, these are these really cool, complex dynamic systems, and we can think about how changes in the marine and the terrestrial spheres kind of combine to influence the sediment and how the sediment organizes, something we call morphology, or stratigraphy, the layers of the sediment in these coastal sinks. And so it's really cool because if we can understand these various forcings and how they influence sort of these modern system processes that we can observe now, then we can study these different landforms and the stratigraphy to hindcast what has changed in the past in both the marine and the terrestrial spheres. And so in particular within coastal sinks, we are really interested in studying salt marshes as sort of these like ideal natural laboratories that preserve changes in the marine terrestrial spheres. And so just to sort of orient you in terms of sort of the anatomy of these coastal wetlands. So here we have like a cross section of the coast, right? And it turns out that elevation is a really good predictor of what kind of habitat type you're going to get. And so at the lowest elevations, we have these sort of mudflats, right, that are exposed at low tides. Moving up in elevation, we have these transitional low marsh systems, which tend to have pretty simplistic vegetation structures. And then at even higher elevations, we tend to have high marsh systems where you might have more complex vegetation structure. These are inundated only with some of the highest tides, right? And then continue to move up, you sort of move into this really transitional zone like scrub, shrub, tidal forested swamps, and then ultimately right here in the forests. And so this is really valuable to think about this elevation gradient because it can sort of allow us to think about how the various controls are acting over these different elevation gradients. So for instance, right, like the lower elevations are going to be inundated more frequently. That makes sense. That also means too that if the inundating water has suspended sediment in it, that's also going to be kind of how we can think about how sediment arrives over the landscape. It also turns out that we have these great curves of biomass production. We think it primarily tends to peak at sort of these like moderately high elevations where salt stress is more limited, but you're still going to have like nutrient input and that kind of thing. And so these controls combine to influence the products that you get. And so these includes things like your dry bulk density or your carbon contents. And I would kind of argue that I think we generally have a good handle on how these different controls affect the patterns that we're going to get in these terms, although you might hear a little bit more about how that may not be true. So at the lower elevations where you have higher inundation, more sediment supply, you're going to have more mineralogenic sediment, right? So the sediment's going to be a bit denser. At the higher elevations where the biomass production peaks, then you're going to have like more organic matter rich sediments and carbon contents, right? But how all these different controls and then also how like changes in carbon content and dry bulk density kind of combine to influence things like the patterns of sediment accumulation rates, which ultimately influences how much carbon you're burying in the system. I would argue those are more poorly established. So thinking more about like what's controlling sediment accumulation rates, our kind of long held understanding is depicted in this image here. So what we think is that primarily in salt marshes, as sea level rises, you must have sea level rise, which maybe is not so true, but as relative sea level rises, it creates something called accommodation space. This is basically the volume within which sediment can accumulate. And like we all know this kind of intuitively, right? Like if you're on the beach or you're on the side of a river, if you dig a hole and water, comes over that hole, it's going to eventually fill with sediment, right? That hole is basically accommodation space. It's a place for sediment to accumulate. So as relative sea level rises, it creates accommodation space. It also increases what's called the hydro period, or the time over which the water spends on top of the marsh. So basically, sea level rises, you're going to have more inundation. And so as sea level rises, as long as there's available sediment, like inside of the water that's inundating the marsh, and there's vegetation to trap the sediment, we expect that the salt marshes will actually grow at the same pace as sea level rise. So if sea level is rising at, say, 2 millimeters per year, which is about the global average, then we expect salt marshes will also grow at about 2 millimeters per year. And so we use this kind of like conceptual understanding of the geomorphology of coastal systems to predict the future of salt marshes and how much carbon they're going to sequester and sort of, that kind of stuff. But when we look at the data, it actually doesn't really hold true. So here is a global compilation of sediment accumulation rates plotted against relative sea level rise rates for a bunch of different marshes. And so if this conceptual understanding was correct, then we would expect all of these points to fall on this dashed line, which is the 1-to-1. But we're not seeing the values fall on that line generally, right? It's not surprising that a lot of these salt marshes are falling below the 1-to-1 line because that means that they're not accumulating sediment at the same pace as sea level rise and they're actually drowning. This is like, the typical story, right, for most of salt marshes globally. What is surprising are all the values that fall above the 1-to-1 line, indicating that salt marshes are actually accumulating sediment much faster than the pace of sea level rise. So this kind of indicates that maybe our conceptual model doesn't really hold true. And the other thing I want to just quickly point out is that this is what a lot of people consider a global compilation. It is a lot of data, but it's primarily from sites that are focused on sort of these passive margins, which means like tectonically not active, right? And also mid-latitude systems, right? So not stuff that's like super cold. And so just to sort of highlight like where we do have data, and sort of this point that we focus on certain systems. So here is a figure that a map of the contiguous US looking at sediment accumulation rate data. And what you can see is we have all this data for the East and the Gulf Coast. Here is a map globally of carbon accumulation rates for different salt marshes. Again, we're focused primarily on passive margins, primarily from the global north. And then this database of soil cores collected by the Coastal Carbon Atlas shows where we have more cores. The colors are terrible. I don't know how I picked it. But for Alaska, there's only 24, whereas you can see like Louisiana is 2 orders of magnitude more sediment cores. which Kendall likes.
I've taken only like 100 of them.
So that kind of leads to like this overarching question, which is how does inundation, sediment supply, and biomass production combine to influence sediment accumulation rates, which ultimately impacts the carbon accumulation rates along tectonically active margins? Are we going to see a different story play out than the passive systems? And so that leads into why we're interested, or at least like primarily one of the reasons why we're interested in studying the Copper River Delta, which is because obviously there are earthquakes here. And that changes the landscape and that changes sea level rise in ways that are sort of like edge case, which is really cool. And so our thought was that if we collected sediment cores from 3 different salt marshes along the delta and measured sediment accumulation rates and carbon barrier rates and stuff like that, that we could maybe tease out what the different drivers are of the accumulation rates that we find. And so the reason why we chose these 3 sites is because we kind of predicted that we would see this variable sediment supply curve, right? Where like the systems that are closer to the main stem of the river are probably going to have more sediment than those that are further away. Right now, this is just an assumption. We're trying to figure out good ways to actually quantify this, which you'll hear a little bit about. And then the second variable that we were interested in is the amount of coast seismic uplift during the 1964 earthquake. So during that earthquake, the land tectonically rose at a couple meters that vary across the 3 sites, with the greatest uplift being at our Castle Islands site and the lowest being at Center Slough. This changes how frequently the system is inundated or the amount of accommodation space, right? Because if it uplifts more, then it is going to have lower accommodation space or lower inundation timing. So the highest inundation should be at Center Slough. And so last summer, we came out and we collected a bunch of sediment cores and did a bunch of different surveying and plant collection and sampling. And we came away with a bunch of data. And so here is just a little bit of preliminary data. So these were what we were terming long sediment cores, although the max was only about 2.5 meters or so. Just like, what is that, 8 feet or something? And so these are 3 different cores from Center Slough, Allegheny Slough, Castle Island, and these are X-ray CT scans of the sediment cores with the shallower sediments on this side and the deeper sediments on this side. I'm only showing about 1 meter in these 3. And these CT scans are very similar to like if you got your body CT scan, right, where you would see your bones that are the most dense generally in your body, hopefully you haven't swallowed anything, would be white, and then the least dense air pockets are black, right? And so this is cool because you can look at stratigraphy. We see this cool layering down here in the Allegheny Slough. We see these weird gas bubbles in the Castle Island core. But the other thing is we can look at the roots and rhizomes and the peat of the salt marsh in the stratigraphy really well from these are 3D scans. But I'm just showing the center slice. And what the first thing that sort of pops out is that the Center Slough salt marsh is a bit deeper than the Allegheny Slough, which is a bit deeper than the Castle Island Slough. So already we're starting to see some interesting differences. The other thing that we can do is we open the sediment cores and we section them at 1 centimeter increments. And then we measured sediment accumulation rates using radionuclides, including excess lead-210. So lead-210 is a naturally occurring radioisotope in the environment. It's part of the uranium-238 decay series, so uranium is in a lot of bedrock. It ultimately decays, it makes its way into the atmosphere, and then it rains out in the environment, and it accumulates in sediments. And so as sediment accumulates, it accumulates down core, but it's also decaying through time as well. And so because we know the rate of decay, if we measure the slope of the lead-210 with depth, then we can back calculate the accumulation of material over time. And so that's what we did. And here's some preliminary data from the Center Slough sediment core. We have excess lead-210 up here in the black points. This is a log scale, so it's exponentially declining with depth, which is good. That's what we expected. And then we can fit a line to this, and the slope of that line, corrected for the decay constant, gets us a sediment accumulation rate, which is 3.5 millimeters per year. It turns out very preliminarily that this is actually relatively fast compared to the other sediment cores. Globally, this is like pretty average, but compared to Castle Island and Allegany Slough, this is a bit faster. One of the other interesting things is the method that we use for measuring the Q10. We can get other radioisotopes from the environment. And so one of those is cesium-137, which is a radioisotope that is human-made. And when it peaks, we know that it was probably either related to Cold War nuclear testing, or what we actually think when it peaks in the surface, it might be related to cesium from Fukushima. And so these peaks can kind of help us also place different time points within the sediment cores. So very preliminarily, what we have seen so far, at least in these longer cores, is that the depth of the salt marsh peat is deepest at Center Slough and shallowest at Castle Island. The accretion rates, super preliminarily, are faster at Center Slough and slowest at Castle Island. And so what we think is that despite the fact that there's all this sediment coming out of the river, and there's tons and tons of sediment in the system, primarily the accumulation of sediment is actually related to earthquake land level change. Super preliminarily.
Does anyone have any like understanding questions before we go forward?
Yeah, I guess I'm a little confused. I thought you said that the further south, or sorry, what do you call it, Tesla had the greatest uplift.
Yeah, so it has the greatest uplift. And so the land rises, then it's like kind of perched like out of the water a little more.
Okay.
So it's the amount of time that it would be spent inundated by the tides is less. Yeah. Is that consistent with what you?
I'm looking at a lot of different maps of the uplift. That's what we're.
Yeah, I would love
That's a
to.
good question you get. I guess when you were, the last statement that you made that it was contrary to what you expected because the accretion rates were highest where there was the least change, but also.
So basically what I think maybe happened was like a subtype, like basically like a mud flat or like a part of the water that was like the bay, like underwater most of the time, like lifted up, and it was now kind of like a mud flat, like closer to like, you know, the surface of the water. Maybe it was like fully exposed when the tide came out. And so sediment started to accumulate there, and it like perched itself at some elevation relative to mean sea level.
And at Castle, it was
And so Castle, I think it was already basically at the top. So therefore it didn't have to accumulate that much sediment to get to the elevation that it wanted to be. Whereas Center Slough was a little bit deeper. And so it had to accumulate more sediment to get to the elevation that it wanted to be.
Does that explain the new marsh, what they call the new marsh over that way?
Ooh, I don't know. Is that the one that's
Where you see all the vegetation moving out?
So, yeah. You wanna,
I think
Talk a
that's
little
really
bit about
what we're trying, like why there's all this new marshland and like how fast that's moving and like what makes it different than like now the freshwater places that were uplifted that used to be more tidal.
yeah.
I think that is where I'll jump in, but unless there's other understanding questions. Did you have a question? I think he's, sorry, I don't put you on the spot, but I saw you asking questions maybe about the field photos. Because I think ERIN didn't talk about how we actually take these sediment cores.
Oh, yeah. So basically the longer cores, we buy 10-foot long PVC pipes from the hardware store. And then we stand on ladders and we sledgehammer the pipes into the ground. And then we use, it's this one, you can't see it. Then we use farm jacks, which, like, you know, if you have to jack your car up, it's basically the same thing. We jack the core out of the ground. But sometimes we also what Kendall does actually is she has to dig them out, which is a lot more work. So I do this. We also have this other thing that's called a gouge auger. That's basically this like sharp metal tube, and it's kind of like a straw that you stick in the ground and you spin it out, and then you get a bunch of mud in your tube. It's pretty great.
You know, George Flacker came here several times and said, have you compared your course with his?
Yeah, so yeah, and actually that's like where we got the uplift rates. Yeah. You go.
I don't want to totally derail you here, but it's interesting talking about sediment accretion here. I think a lot of people, you know, flush around the flats and familiar with Copper River, have always wondered how deep is the sediment out there? And obviously you guys have a limitation with what you can do, but
Yeah,
you know, there's so much sediment coming out
Oh,
of the
yeah.
Copper River for so long. I've had several conversations in airplanes or on the side of the river or whatever, like, oh, I wonder how deep this ledge is, you know? And do you
yeah.
know anything about that?
So we can't for sure say how deep the sediment is because the pipes are only 3 meters, and I suspect it's quite a bit deeper than that. In fact, we were thinking before while we were doing our initial planning, that we were a little bit worried that the marshes themselves would be deeper than 3 meters. But you know, like that's the easiest pipe to buy at Home Depot, and yeah. It turns out that the depth of the marsh is actually not that deep. I mean, you saw in the CT scan, it's only like at max like 30 centimeters or so, which I was pretty surprised about. Yeah, but it would be cool to do some like deeper surveying and see what else. And one thing that is frustrating actually, so comparing to the previous cores that were collected, so with the 3 meter long pipes, we have to stop at like around 20 centimeters exposed because we use this like pipe jacket. I don't think we don't have a picture. We use a pipe jacket that allows us, it like clamps onto the PVC that then we connect to the truck jack, and that allows us to jack it out. If we had gotten those 20 centimeters, I think we would have gotten the preceding earthquake based on the depths previously recorded. So that was a little frustrating, but.
So back in 73, when I first got here, there was a soil scientist assistant, Bill Quirk. And he sampled all the way out to Castle Island. So we have all this sand blowing down river from about October until April, depending on the snow cover at river.
Uh-huh.
But there's consistently wind from late October onward. And he found up to 7 inches of sand and silt being deposited on Castle Island.
Wow.
So pretty heavy deposition.
Well, okay. So obviously I don't have the accumulation rates for Castle yet, so I'm really excited to see that. So like the lead 210 that allows us to measure the accumulation rates, like I've been going deeper than what we have the marsh in all of the cores because we're still getting activities that are above detection limits for the instrument. So you can see here, right, like we go almost to 50 centimeters. I'm pretty, obviously the data is more sparse, but and there's a little bit of wiggle. The R squared is still pretty good. I'm surprised at how constant the accumulation rates are, at least for this salt marsh, but I'll be really interested to see if I get something that, you know, much faster accumulation rates below the surface sediments. Because, you know, because you could imagine like it accumulates really fast, really quickly, and then it you know, reaches some like optimum elevation for the salt marsh to grow, and then it's kind of in this dynamic equilibrium.
Yeah, and the other consideration is our winters are becoming more mild. There's less ice accumulation and thickness from let's say December into April.
Mm-hmm.
So there's more coastal elevation. If you go back to one of the slides that shows Center Slough, Alleganic, and Castle. So I live, if you look at the word center, if you move the C and E right, to that big bay right there.
Okay.
Actually a little bit more left.
Oh, okay.
So that's Sunny Bay, and the next bay over is Goose Cove where I live. So my place is on the beach ridge, the old beach ridge, which is gravel, and it's now covered with mostly alder, but also spruce and some cottonwood actually too.
Yeah.
And then out in front, there's at least 200 meters worth of what was sedge grass flats back in the 80s when I bought my place in 81, 82. And now that marsh is now a flooded shrubland. So it's pretty damp out there, and the outer 20 to 30 meters or so is sedge. But then you come back and you pick up sweet gale primarily, some alder, and then quite a bit of willow too. So instead of being a great flat for geese to graze on, it's now suitable for moose.
And there is some evidence too that the moose eating the sweet gale causes.
Well, deer eat sweet gale.
Right?
I don't know about moose.
Okay. So you're saying that the whole system is like growing out more and becoming more complex vegetation.
Well, yeah, in terms of vegetation advancement
Yeah.
out towards the coast. But the other factor is that beach has eroded a foot a year over the last
Yeah.
40 years.
This is, we were talking with, a gentleman that we, Mike Mahone, that we, is taking us out tomorrow. We were talking with him in Hartney Bay, and he was telling us about these sort of like, you almost get like, coves of erosion, like hotspots of erosion right next to hotspots of deposition.
Right.
And that's like a fair bit of what that like modern surface processes is a fair bit of what KENDALL studies. I don't know if you want to.
Yes, I can jump
Yeah.
right in. Yes, I'm glad we're good. I just know sometimes it gets
Just one other comment.
exciting. Yeah.
One other comment. We have these storms that come through from the southeast. And then right at the end of the storm, it'll start blowing westerly. And that's when these storm tides really build up. And I think that westerly exposure that I have on my beach really causes a lot of erosion. Whereas Castle Island is protected by these big sandbar islands. I don't really have that protection. I have Hitchenbrook Island, which is 6 miles away from Boswell Bay, but there's just a little bit of Little Egg Island
Yeah, right.
protection. And then Big Egg Island is
Mhm.
really of no value to my beach, but it is as far as center still goes.
Well, so that's actually super valuable because something that we've been wrestling with is trying to determine what the sea level, like the modern relative sea level rise rates are across the delta. And that like wind setup is really difficult to sort of tease out and could be one of the reasons why the elevations are kind of showing an opposite pattern that I think Kendall might talk about. That we think that maybe water is piling up preferentially in center slough, maybe because of exactly what you're talking about. Cool.
Yeah, wind is a very powerful movement. We actually haven't thought that much about wind yet. But it can do a lot more. Here, the tides are so huge that it doesn't make sense. But I did a lot of work in Louisiana and the tides are this big. And so the wind movement actually is way bigger than the tides. So you never check the tide charts when you're going out on the boat. It's always to check the winds. Got stuck one too many times. All right. So, well, I'm glad we got there. So what ERIN showed you is a lot of really great stuff about kind of marshes in general, but when you're out in a marsh, you see a lot of spatial variability, right? Like it's not just one flat marsh with all the same vegetation. It's not the same like elevation everywhere you go. The first time I was in a marsh, I was 5 years old. I went on like just for fun, and that kind of kicked off this whole thing of thinking about how different they are everywhere, and like why. Why should one place be eroding faster than another? Why are different plants growing in different places? And that's kind of kicked off my whole career. And so this continues our same overarching question, thinking about inundation, or basically how often the marsh is flooded is one of our main controls and what we think is driving a lot of the processes we're seeing here in Alaska, but in ways that most of the rest of the world does not think about salt marshes. And so to give you an idea of like what happens within a salt marsh, this is the very simplified diagram of what goes on. And so really it's the interactions of the physics of the waves, tides, and currents mixing with the hydrodynamics of the actual sediment particles getting on top of the marsh. And then it's the vegetation, which slows down the water, traps the sediment, allows it to deposit. The plants themselves then also like to be flooded a certain amount of time. So they like to be at an optimal elevation. If they're flooded too much, they die. If they're not flooded enough, they turn to more terrestrial things, right? Terrestrial things outcompete them. And then the roots of the plants themselves hold the soil together. And so this is kind of a like very complex system that tends to like sit itself right at a certain level related to sea level, right? That's why like marshes, that like the kind of grasses you see kind of are always sitting where they get flooded, you know, most high tides, or at least one high tide a month, I think is kind of the minimum. And so these complex interactions then also drive why you see the spatial variability across a given marsh. Some of the data I'm going to show here are from my graduate student, Kendall Fontenot. Yes, we're both Kendalls. So it's easy to remember. You have a good chance of getting our names right. But this is some pictures from last year when we had beautiful weather up here. But a lot of what we do is we use this RTK survey system. So basically, same as construction equipment, like you measure elevation to like sub-centimeter scale. So we can get like how the slight variations, like to most people, this looks flat. To me, it looks actually very not flat, especially compared to places like Louisiana or Virginia coastline. So those small variations lead to a lot of differences. And then the other thing that we do is we take these short sediment cores. So yeah, it's pounding in with the sledgehammer. I dig them out because I like to get in there with the plants. And then also doing vegetation surveys. And then we actually dig through here and separate each individual root and figure out the structure that can tell us how strong the sediments are, how that's leading to biomass accumulation, all of those fun things. The field work's really the best. We were out in Hardy Bay or most of the day today. So what we've been finding, so last year we went and took a ton of sediment cores kind of more across the gradient. Instead of like one deep sediment core that ERIN was talking about, we're taking a sediment core kind of moving in the elevation gradient so that we'll see a change in plants and see how the marsh functions in different places. And so here's to give some idea. So we were looking at these same sites. We also went to 3 Mile Bay, not too far from where we are right now. And so if we look at these, the colors are indicating the average elevation of marsh. So we went and took like hundreds of points on marsh, take the average elevation, and we see that basically there's a pretty good gradient of elevation as we move across. That's really related to some of that the plane from the earthquake, right? So that uplift relates to that. So, and then we can even look at that, and we've looked, this plot is showing how much organic matter, basically how much carbon is in these marshes. We haven't really explained why we talk about carbon. Many of you probably know, but just as a quick aside, marshes, one of their key ecosystem services that people value is, well, one is like habitat for animals and birds and all those things. Those are all great. But carbon storage, or basically taking carbon from the atmosphere, becoming plants and then being buried, is a really valuable market right now, and also good for the environment as a whole. So that's like why we've been focusing a lot on organic matter. It also tells you how well the marsh is working. But basically we see that the amount of organic matter or how much carbon is within those sediments is really dependent on the elevation of your site. So it's basically how frequently it's being inundated is affecting how the plants are behaving and then storing that carbon. And so this is across the whole delta, like we've been talking about. Well, let's zoom in on one site. So we spent a lot of time at this site at Center Slough. So this was that like most western site that we were talking about. And so we're going to zoom in here. This is kind of the main marsh land here. On one side is the EOC River. We have the bay over here, and then we have Center Slough is this tidal creek that's coming up on the marsh, right? And what makes this really special is those different places are going to flood the marsh differently, right? We said that inundation is really important. Well, the bay is going to flood it when storms come in or you have regular tides. The tidal creek is going to be flooding from just regular tides. And the river is going to be flooding more seasonally and depending on things happening in the mountains, right? And this is what distinctly is not happening in most other marshes that people study, is this like huge river changes right next to a marsh. So we went out there and took a ton of sediment cores and elevation. So you can see the colors here are elevation. So you can see when you're closer to the bay, it's lower and you basically walk up the marsh, makes sense. By the time we got up here, we were in shrubs and decided to avoid bears. So we stopped there. And then, so that was a very expected trend. That's like all the pictures, like cartoons that Erin showed you, were showing you get higher as you go up. I think most of you would intuitively think that too, like we've been outside a lot. But what was more interesting is that we went across this east-west transect, and there's actually a huge difference in elevation, like almost a meter actually when you go across. But just from like where I would expect it to be relatively flat, it's not, it's tilted. And that was really surprising. And that means that like these different inundation or flooding regimes are changing the marsh and how it's working, how it's storing carbon. So then we also, at all these white circles, we took those short sediment cores, dug them out, and took a good look at what's in there. And one of the things we can do is actually look at the sediment that's there. So who knew that they're like, you can split sediment into lots of different size classes. So basically we take what is like, just looks like dirt, and separate it into sand, silt, and clay. So sand is like what's in your sandbox. Silt is in between, and clay is really tiny particles, like 4 microns big. So we're talking like cell size, right? And so on this plot, I'm showing on the x-axis is grain size, sand being over here, clay being over here, and the y-axis is volume, or just how frequently it occurs. So where you see a peak, it means it's dominated by that type of sediment. So we look at the river core, so this yellow one, we're going to move river to tidal creek. You see, there's a huge peak in sand. So the river is actually delivering a ton of sand to the marsh, right? And on the other side, you see the darker color, the tidal creek site. There's basically no sand present, but we see a lot of mud, a lot of clay. And so this is showing it's not only changing the inundation, but what is actually being brought to the marsh. And from all of our understanding of marshes is, first off, that sand doesn't really store a lot of carbon, because carbon likes to stick to mud, just like mud likes to stick to you. But it doesn't really like to stick to sand. But also, almost every marsh scientist I would know would say that there's no sand in marshes. So definitely not true here, which you guys probably already know. And so this is looking just kind of an average of the whole core, that there's sand there. But if we wanted to look at it down core, so looking back in time as we go down, I'm going to show you, this is a sediment core. So this would be the ground going downward. This is on the river side, moving towards that tidal creek. And the black is sand, the gray is silt, and the white is clay. All I really want you to see here is on this river side, you see these big black like triangles that are connecting across the marsh. These are lenses of sand that are basically being pushed across from the river. And they actually get all the way to the middle of the marsh, but they do not get over to that tidal creek. So they're making it a few hundred meters, but not all the way there. With me?
Are you gonna try to correlate those with storm events, or?
I think the seasonal flooding event, and looking at river discharge, I think is the most likely thing happening here. I think the other thing, this one could be related to the earthquake, but we're just not quite sure yet. That's the only other thing, because like there was very large grains in there that actually couldn't fit in my grain size analyzer, so that should actually be even a bigger number. So the presence of very large grains would indicate a really energetic environment. So basically, oh, go ahead.
So in September, when we get a lot of rain, some years, like September 9th or so, maybe clear through the end of the month, it might rain every day, like an inch a day or so. When we get these really high tides with a southeast wind, I could see that silt coming out of Yak River could be blowing westward. So you'd have a pretty thick to a thin gradient, like you show up here at the top 30 graphs.
Yeah, and there's like huge changes in when you have the discharge of like what the grain size is coming out to, right?
Right.
The silt, yeah.
But then later on in October, when like Power Creek, which is the main source of Yak Lake, clears up, you're not gonna have much sediment coming out there.
We haven't looked at that.
Yeah, so there's quite a change from August to September to
The
October.
sediment supply of the river itself.
Right.
Yeah, well, it's also, there's like what's coming down, but also what is locally picked up as
Right.
it's like coming down there, and like as it meets the freshwater and the saltwater will lead to turbulence, which leads to enhanced erosion in that spot. So but we've been looking more at the copper sediment loads, but I don't know as much on the Yak sediment load. It's a really good idea.
I wanted to talk about something that Pete mentioned earlier. That's about the wind transported silt coming down the main stem of the copper. No, it's really localized. I mean, there's obviously when there's a north wind event, it's blowing out of those other valleys as well. But the copper, because it's this channel that goes all the way to the interior Alaska, you get more wind speed down there and so more transport of sand and silt. And I think that could be a pretty large amount in comparison to the stuff that's transported by the river. It's not going to equal that certainly, but I think it's substantial and needs to be considered.
That's, and I think
And
Sophie
it
has a,
affect that Castle Island site much more than your other two sites.
I would
And
absolutely
intuitively,
agree.
just because it's so localized down the main stem of the copper. The wind is just fierce down there in the winter at times.
I have a follow-up question. So yeah, Sophie has a picture of it because we have been thinking about this. She'll get to the satellite picture. But I was wondering, when it's coming down, like how much snowpack or ice pack is there? Like, is it all falling down on, like, is it able to reach the ground? Or is there like an intermediate step? I guess that's a good question.
Sometimes there's a lot of snow out there and sometimes there's not, even in the middle of winter. But you can just go out there to the main stem of the copper, and if you're able to travel downstream or fly over it, you can see the dunes. There's some really big dunes that are as a result of that winter wind, that north wind, pushing sand down the river. Yeah.
So in October, when these winds start, they're around the 20th of October, so they're blowing 30, 40, 50 miles an hour down the copper. There isn't much snow, or if any, on the ground, and if it does fall, it's still fluffy enough that it'll blow off, so that sand will deposit from there all the way up to middle of the island, actually. So once we get snow at the Copper River, which would be, say, mid-November or so, all the sand that's coming down is going to go right on the ground or get blown further out to sea. And then we have this snow cover that's generally permanent with bands of sand and then more snow bands of sand. So it's layered. There's different bands of sand. And of course, when that melts out in May and June, that sand drops down to the ground.
It's definitely.
And the winds are just horrendous. I mean, they can be blowing 80 to 90 miles an hour easily up there in the middle of winter, clear into late March at least.
Get me out in the field there. No, I think that's absolutely something we should like. Well, we know we have been thinking about it, but something that's like some of the next steps we'll get there with. Sophie, but any other thoughts there? I don't want to keep you too long. We doing okay? Okay, not too boring. All right. So yes, we have the sand coming in. And this one is from Center Sluice. We're further away from this wind influence, but it probably is still impacting. And also if it delivers sediment to the coastal ocean, then it still can be reworked and brought up here. So even if it could be coming down from the winds, depositing, and then moving its way over, which is another fun thing. If only we could put little Apple tags and listen to watch where it's going. People actually do that with gravel, which is pretty cool, but much harder to do with sand and mud. So we see these lenses of sand coming across, and we can see that sort of reflected in our organic content. So here, this is basically the cores again. So this is the surface and going down, right? So like we take all of those cores and we take them over ground, we cut them into 2 centimeter sections and we like really dig into them. And on the x-axis here, we have percent LOI, which is basically percent organic matter, how much carbon or living material is in there. And so just like we were talking before, we would expect that like near the bay, we have lower organic content because it's really harsh and plants can't really grow there as well. And as we move upland towards these pinker colors, we're going to have more organic material. The plants aren't as stressed, they can be happier, we can create more biomass. But what was really cool, more of like the spatial variability on that east-west direction, or just knowing that there's basically different flooding going on here, is that on that river side, this yellower color, there's lower organic matter, which is what we expect from sand, right? Carbon and sand don't like each other. And then when you get over to that tidal creek, we're getting more and more organic matter. But this is all within one marsh, like not that far, like, you know, an easy walk. And so it's really hard to get an idea of like what one number does for a marsh. And so this create this sort of, well, this beautiful, this is kind of other Kendall's figure. This beautiful idea of basically these two different flooding influences driving lenses of sand and mud coming across the system, leading to a lot of spatial variability. It also means like different use by different animals. So, marshes are great habitats and nurseries for baby fish. And so, the access to these planty areas where there's a lot of bugs, when the water floods, fish can have access to these lands. And you can see by this elevation gradient that we'd expect that the fish would actually have more access from this side compared to the other. Right, so it's not just, oh, it's creating sand versus mud, which is what I find fascinating, but other folks might think more about animal usage of this space, right? And birds also would like certain types of habitat and how often they're flooded. And so that's how we can expand these kind of ideas. I'm gonna leave you there and I'm gonna pass it off to Sophie.
Perfect, thank you. Okay, so we've talked a lot about sediment. We've talked about how it moves. We've talked about what kind of sediment is being deposited. Talked about where it's being deposited. Talked about how it's changing over longer time frames. And so sort of some of our next questions become, one, where is that sediment actually coming from? And what is actually in the sediment? And how does it impact things like nutrients or pollution? So that's where I come in. So I'm the geochemist in this group. I study kind of all things trace element. And so on the board, this is kind of a complicated figure if you're not used to looking at geochemistry figures. But sort of the central idea here is that you have depth. So more modern sediments or more modern samples up at the top, going down in the core, down back further in time. And sort of all four of these colored lines, the first four of these, essentially are showing these ratios of different elements. And each of these elements is essentially a tracer or a fingerprint, much like your own fingerprint, of where sediment is coming from, either from sediment sourced from the Copper River or sediment that's being sourced from Prince William Sound sediments that have deposited. And so what we can do is we can basically take what we expect sort of those ratios to be, and we can feed them into a mixing model that tells us then how much sediment is coming from each of these sources. And so one thing that's, maybe unsurprising for this site, this is at Center Slough, is that almost always we have about 90%, 90 to 95% of the sediment that's coming from a Copper River source. So it's coming from upland moving down. However, during very specific periods, highlighted in gray, we see that there's a change. And there's this significant change to about 80 to 85% of the sediment. And so we get a drop or a distinct change towards Prince William Sound sediment. And if you connect that to the age dating that ERIN's done, we can actually see that some of these sites are exactly lined up with when the earthquake happened. And so basically, because we have this change in all of these ratios, we can suggest that the earthquake essentially created a plug of sediment that was coming up onto the landscape from Prince William Sound. And that's maybe not surprising, right? You have big earthquake, big changes, lots of changes in the water, lots of changes in turbidity, lots of changes in sediment moving onto the land. And in fact, that's been seen before. So this is another paper from some folks at VIMS that did some work out on the shelf instead. And they used the same sort of ratios, same sort of idea to look at these earthquakes. However, because they're out on the shelf, these are essentially from gravity flows within the Prince William Sound itself. And so you basically are taking a core from where the slope edge is. And so any time that there's a gravity flow or sort of like a mini earthquake underneath, that you have this sediment that's traveling, it's going to be deposited over the top of your core. So that's under the water, sort of at the edge of this, this angled break, right? But here we're up on a land surface. And so we don't have sort of that gravity flow from the Prince William Sound. Gravity goes the opposite direction if you want to get things up there. So it could be that we have more tidal influence, but what's particularly interesting here is essentially that this is not a quick thing that happens. This band here is about 15 years. So that deviation and that change in the sourcing of sediment is actually something that's happening for a longer period of time. So this isn't this happens once, you get a big plug of sediment, and that's it. This is something that we've fundamentally changed that bottom water condition and that bottom sediment condition such that we're actually transporting more Prince William Sound sediment up onto the mudflat for about 5 to 15 years, depending upon that band, post-earthquake.
How do you tell the difference between Prince William Sound and just sediment coming down the rivers?
Great question.
Not Copper River, but the local rivers.
That's a great question. So the Prince William Sound sediment is composed of a mix of many sediments.
Yeah.
So this data is basically saying so this paper here, there was some work done within this paper that basically did work tracing the ratios of these different elements to one another for rivers upstream of Prince William Sound and the Copper River. And so all of that feeding into the Copper River, all of those sediments were basically sourced from all of those different areas. And so that Prince William Sound sediment is basically it's a composite. It's a mean of all of these different sources aside from the Copper River. And the ratio and the variability is actually quite small compared to the ratios from the Copper River. Copper River is really interesting.
Yeah, but our local source rock
Yeah,
is Prince William Sound.
right.
Copper River is a very different source rock.
Exactly.
So,
And that's why
so
it's so
when the
different.
earthquake happens, you get that lift. Now all of a sudden the Eyak River, the Allegheny River, all those local rivers are really able to deposit a lot of sediment from very nearby. Rather, when you say Prince William Sound, my mind automatically goes out and then comes back.
Absolutely.
Instead of it being a local sediment versus a Copper River sediment.
Yeah, that's a really good point. And that is something that would be interesting to look at the specific sourcing within the rivers themselves. So within the rivers from these smaller rivers that are really localized to the area that we're looking at. So like this one is from Center Slough, right? So this is a very specific site. So looking at the Eyak would be really interesting to see if there is, so maybe that's the difference. Maybe it's not coming from Prince William Sound, maybe it's sediment that's changing because of changes in the Eyak. That could very well be. Yeah, it's a very good point. Great question. Thank you. That's a really good thought that I hadn't had before. And so, yeah, I mean, the big takeaway here is just that these earthquakes have a much longer effect than we maybe would think from their sediment sourcing perspective and where that sediment is coming from. And so you'll have to excuse me because this is data that I collected about 3 weeks ago, and then I went into the field 2 weeks ago. So, so this is all very preliminary. However, I will just add a couple of further sort of geochemical questions that are sort of itching at my brain. So one is this sediment sourcing across the delta beyond just Center Slough, but to look at Allegheny and Castle Island. We also have the sediments from now Hartney Bay as of 8 a.m. this morning, and as well as 3 Mile Bay. So being able to do the geochemistry sort of across this gradient is particularly interesting. The other thing that I am particularly interested in my geochemistry brain is looking at the impacts of these massive dust storms that happen every winter here, right? And so these dust storms carry a lot of iron within the dust itself. And so iron is a very important nutrient. And so if that iron is making it to the delta and being deposited, what are the impacts of that iron? And so part of that question is understanding sort of the bioavailability of the iron that's in the marsh. So how much could plants and animals and phytoplankton basically use that iron that's in the marsh that's potentially leaking into local creek areas and tidal areas. And so this is some very, very preliminary data. And I'll just highlight, so this is the iron to aluminum ratio. That basically means how essentially looking at the iron concentration relative to what we would expect it to be in bedrock. So higher values are meaning essentially it's higher than upper continental crust, which is sort of an average value. But what's interesting here, and something that I think is particularly interesting with the questions that KENDALL asks related to sort of this modern process and sort of spatial variability, is being able to look at, so you'll notice that the peak in the iron concentrations here essentially happen within the first about 8 centimeters of our core here. And part of that, there's been some linkages between the impact of plant material and root material and iron cycling. And so this is a question that is really interesting, especially when we're thinking about, say, you know, the impacts of sand versus clay, the impacts of sort of these river versus creek sites, and sort of being able to do sort of a more complete sort of spatial analysis, as opposed to only doing, or in addition to doing, the deeper records to look at change. And then I'm also very interested in pollution and seeing how pollution is kind of propagating within the delta, if it is, if it's not, because that has a huge impact on potentially bioaccumulation of pollutants in things like fish or clams. All right. And so here's sort of the big takeaways of this work, and then we'll break and ask for more questions. But sort of our big takeaways here: 1, accretion is controlled by inundation. Then you have this inundation that's happening from these rivers and tides, and that provides a distinct signature within the marsh. So KENDALL talked about sort of those lenses of sand that are happening. And then that sediment that then is delivered during inundation has a distinct source and a distinct biogeochemistry, and those are things that we're interested in. And then, because this is preliminary work, we've been doing this for about a year-ish, a year and maybe 3 weeks. This is very much in the preliminary stage still. And so we have a lot of continuing questions or continuing curiosities. And so one question, and we'd love if anybody has thoughts on these questions or other questions, we'd love to get your take on any of this. One is sea level falling or rising across the delta? The next is a favorite of KENDALL's, which is how is ice really influencing the marsh? And then finally, how does that sediment delivery and source influence the nutrient biogeochemical cycle, which I already kind of introduced and teased earlier. All right. With that, we'll kind of close. I want to get to people's questions. Yeah.
I have a question. We were discussing wind on the Copper River corridor.
Yes.
And I work out in the field there and I'm very familiar with all the deposition that can occur over the winter time from that wind-based sediment load. Is there a way, a technique to differentiate between waterborne versus aeolian deposition? And like, yeah, I guess I'm just curious how that works.
I think the easiest way is to look at the grains of sand themselves and the shape of them. And so grains that are more transported by wind tend to be rounder than those transported by water. And they also tend to be a little bit better sorted, so more like the same type of grain sizes versus in the water, you tend to see more of a spread. That's like the rule of thumb, but when you're like going to say how round a grain of sand is under the microscope, but I think that would be like kind of the first pass effort, and that's I've been saving the sand that I've been pulling out to do that analysis to try to get a hold of that, but it's quite tricky because also any sediment that's around in the creeks longer also rounds over time, like as you know, you imagine just bounces around and is becoming more compact. So that would be probably the first way to try to address that, because a lot of our like dating methods don't work on sand.
The only other one that I know of is you can use optically stimulated luminescence. So basically sand particles remember the last time they saw sunlight. So if you take cores and then keep all the sediments dark, and then you do all your analysis in a room, and you can use red lights only, so they're creepy labs. But you can then excite that same like photon reaction, and then you can figure out how old, like when's the last time they saw sun.
So transported sediments would have a more recent sun.
Yes, you basically kind of can get age dating similar to like using the lead method, but lead doesn't work. So, but that's tricky and much more expensive, and yeah, so I don't like the red labs. I've done that.
I wonder if you considered, if the land in portions of the delta might be rising due to the glacial melt, like glacial rebound effect.
Yeah, so like the way that you calculate relative sea level like incorporates things like deep uplift or deep subsidence because of changes of the plate relative to like how it sits on the asthenosphere. So exactly what you're talking about. So I think that's
What I'm talking about is actually independent from earthquake activity.
no, yeah. So right, so like when the glaciers are sitting on land, they make it sit deeper within the asthenosphere, and then when they melt, right, like get like that interglacial rebound. Yeah, so that's part of it, plus the tectonics. Then the weight of the sediment is also going to affect like subsidence of the whole delta. We think we can probably tease that out. The part that I'm like trying to wrap my mind around is actually more like the physical oceanography and how like water masses piling up in different parts of the delta might affect the relative sea level like long-term trends, but then also obviously like, the seasonal is going to be important if the sediment supply is super seasonal as well. Because like we in work that I used to do in Oregon, which is like the rivers there are super seasonal, 95% of the water in the sediment all comes out in the wintertime. You can kind of get this disconnect where like when there's a lot of sediment in the system, like if that sediment doesn't get onto the marsh platform, like the marsh is not inundated, then like it just totally bypasses. And so we have some salt marshes there that are like appear to be not sediment limited, just solely based on like a mean value of sediment supply. But then if you actually look at like the internal marsh dynamics, like they actually are sediment limited because none of that sediment, it just all bypasses the system and like sort of shoots out. So yeah, it's like that. Yeah, we're thinking about that as part of the equation. We're thinking about that as part of the equation. But yeah.
Like even in New England, they still have the rebound happening from the melting of the glaciers. So here it is definitely way more important.
Yeah.
But yeah, but that is a cool thing.
And I'm not sure if this is over by the center sloughs too, but Allegheny, we always hear about the lost or the drowned forest from 800 years ago. So I would think, that would have, that's why it's perched there. That's why you're gonna have a whole different sedimentation. It's probably gonna be different from Castle. I mean, I can just see all this variability between sites. It's not like you're dealing with a control site anywhere.
Yeah.
Because of things like that.
Yeah, it definitely makes these like natural laboratory experiments a lot more challenging. Our hope is that we could maybe collect more cores kind of like on this transect and sort of start to like see these general patterns emerging better. Like attempting to account for like all that like very site specific.
And are you starting, if you start at the shoreline, are sort of, how do you do it? Do you always start at the shoreline and then go so far in?
It depends on like, sometimes we'll walk in from the, like for instance, Hartney Bay today, like, we walk down the slope and through the forest side, but we like to go all the way along the transect before, like we kind of, using aerial photography and stuff, we like sort of set out what we think we're going to do, but then we go out and like oftentimes totally changes based on like walking the transect. Like today, for instance, we walked it and it didn't sit right. So
Do we talk about how you choose the transect, like where we start, where we end, kind of thing?
Well, we try to look for like when there are weird things to avoid. But like sometimes, especially like we don't live here, that's one of the joys of meeting you all is to hear more about like these really, if we can't obviously see them, like what is a weird thing that's going on here.
'Cause
But then by having like more samples, you kind of can average out the weirdness. But then we also look, like, I focus a lot on trying to control for the hydrodynamics. So today it was like there was a little fringing marsh in front of where we thought we were gonna go, and that's gonna slow down the waves. And so I was like, oh, that's not gonna be the same as all the others. So I think we switch a lot based on looking at, I like the edge the best. Get the most muddy out there, and then we work our way in.
But you know, that brings up your three sites have very different hydrodynamics associated with them. You know, and so the very simplified model that you provide and you say earthquake, it's your whole morphology on all of those sites and your hydrodynamics are so different. Why do you think it's the earthquake and not local factors that are bringing in the differences that you're seeing?
Yeah. We have to look at it more. I think some of the, like those barrier islands, right, provide like a block to like big swell waves and things like that. So a lot of the sites we picked, we know what the maximum distance like local winds could blow and create. And like I do a lot of modeling, and we can model what the maximum wave heights can be. And so we can kind of know that within those have a set distance between, and so we can kind of estimate that they all have relatively similar wave impacts on marsh edges. There's a lot of other problems, but that like one of the things I look for on especially with the edge sites, so that way they're having very similar wave climates.
Yeah, your freshwater flow is so different.
The freshwater flow is one I think we're still trying to get a good handle on.
That kind of led perfectly into my question, which was, have you looked at the barrier islands at all? And what variability there is kind of along that same directional path from east to west?
We have not yet. We have been wanting to get out there and have not yet been able to. But we want to. That is something that we're really interested in, sort of that similar sort of directional question. And then those barrier islands are great.
I was curious because just anecdotally, I stopped on one east of Egg Island a couple weeks ago, and I should have brought sediment samples back. I wanted to, but I also wanted to bring the entire beach back. So but it's the softest sediment I have ever felt on a beach in Alaska, and one island over, it's not the same. I don't think. It's
Interesting. That's cool. That's very.
That's slide 3 slides back when we were talking about the chemical ratio between Prince William Sound and upper rivers. What's the, so looking at the, the far right orange dots here.
Yes.
Looks like there's a mid-80s event.
Yes.
Any thoughts on what that, we're talking about earthquakes, what's going on?
There was an earthquake that was over 926 that did have a impact, and you see it actually in the, yeah, it was 1983. You can see it in the gravity flow as well.
Okay.
And it lines up well with our age dating. Yeah.
Just have an observation, but the, I don't know if you. Being on the Allegheny River, I've noticed a lot of floating sand banks. So that as the tide comes in, you'll get these mats or bubbles of floating sand. And, you're on it, your paddle goes in, they all fall out. And I was just kind of curious about that as, a mobility factor in sand, being pushed with wind, maybe to the east.
Do you think it's a hypopycnal flow? Sounds like it. Is it dry?
Yes. Basically like dry sand. I don't know if there's a biofilm or some sort of film that's.
Yeah, so
making it float.
So sometimes the biofilms, because they're photosynthetic, so then they create bubbles, which helps it float. And sometimes when they mature enough, they detach to propagate themselves. And so I have biofilms on my side friend project because they're weird. It's all the goop on the so it's lovely that you brought it up. But basically, yeah, so what I've seen, and I grow them in the lab also as a side project, but yeah, when they get mature enough, those bubbles become big enough to like rip them off, and then they just like float. And I think it's a way when they're, when they're too mature, there's no more space for new ones to grow. So it's beneficial to them to like pick up and move. but they can't walk. So
Right.
that's so cool. I've seen some of it in more the Caribbean, but
Okay.
very cool.
Yeah, the alligator just gets big somewhere.
Big.
It goes way down the main. Towards the 22-mile bridge.
Yeah.
So it goes all the way up into there and I could.
When we were-
15-foot tide.
And we were up there was fog and you couldn't see like further than this, and I don't know how Sean gets out there. We only, that part was amazing. But yeah, that's really, really neat. Thanks for that observation.
Before we keep going, I just want to be cognizant of time. It is 5:40.
6:40.
It's 6:40. So if anybody needs to leave, we're happy to keep chatting, but we also want to be cognizant of people's times.
Captive audience.
That's great. We're also a captive audience. But
Thank you.
Thanks for listening to
yeah,
us.
thank you so much. Yeah.
If you have questions, don't talk to them.
You can talk to us or you can find us.
Yes.
Like we're happy to always chat. We want to learn more.
So you could filter the local river waters and get the same ratios to see if it's.
Yes, we drove over every bridge along like past the towards the airport.
I'm trying to, it's one of those things that, I'm kind of curious about how I thought it because
Yeah.